Okay, friends, so we continue to figure out how hyperbolic geometry works. Permit me to bring this theorem to your attention. So we will assume that L is a line and P is on line M, but not line L. There exists at most one point Q on M, not P, the same distance from L. So we'll let P prime be the foot of the perpendicular from P to L. There exists at most. So here's what we do. We assume that there is at least one, and we try to show that there can't be more than one. So to do that, we say, what if there is? What if there is? What if this distance is this distance is this distance? What's so bad about that? Well, what's really, really interesting is that if this is the case, then quadrilateral P prime Q prime Q is a Sakari or Chi-M quad, and quadrilateral Q prime R is a Sakari or Chi-M quad. Well, what's so bad about that? Remember about the summit angles of a Sakari quad. This is an acute angle, this is an acute angle, this is an acute angle, this is an acute angle. Oh, looky there. Angle PQQ prime is supplementary to angle RQQ prime, which means they both cannot be acute. This is a contradiction. Where did we go wrong? By assuming there was another point R that was the same distance from L that P is from L. So there can be at most one point Q that is the same distance from L. In fact, this goes in a similar vein. If line L is parallel to line M, and there exist 2 points on M that are equidistant from L, so, right? Then L and M admit a common perpendicular. What does it mean to admit a common perpendicular? That means that there is a perpendicular line to L and also to M. There is one line that is perpendicular to both L and M. Do you see it? Do you see what kind of quadrilateral P prime, Q is? Do you see that? Yep. The base angles are right angles. Those are congruent. This is a Sakari or a Chi-M quad. And you proved in a previous lesson that if you connect the midpoint of PQ to the midpoint of P prime Q prime, you get a line that is perpendicular to both the summit and the base. And that's how we prove that. Common perpendiculars are unique. Well, that should be straightforward. You got L, you got M. They admit a common perpendicular. That has to be unique. What goes wrong if there's a second common perpendicular? Well, then this shape doesn't exist in hyperbolic geometry. There is no rectangle in hyperbolic geometry because there is no quadrilateral whose angle sum is 360. So because this can't happen, common perpendiculars are unique. I've got one other theorem we should talk about. That'll come in another video. That's it for now.